So yeah, it's my great pleasure to introduce Sudharshan Suresh for his PhD defense today. So Sudhu has actually been at CMU for quite a bit. So he was, not because PhD took long, but he was a risk scholar here originally for summer. Then came back in the master's program, and that's when he joined my lab, working on underwater robotics. And localizing robots underwater by looking through the water surface, actually, looking at sealing, for example, at structures. And then when he applied for PhD program, he told me he wants to do tactile perception, which is a pretty hard turn from there and something we didn't really do in my group. I was interested in, but we didn't have the expertise. So I was a bit worried at the beginning, but knowing him at that point, I thought, okay, let's try this. And so Sudhu actually reached out to a number of people at the time to connect to experts on the tactile side. And so this started a number of relationships. For example, with Alberto, who is one of the external committee members, and also with Nancy. And so that's how we got to today. And so there's a lot of quality work in the meantime, recent submission to Science Robotics, actually, on the work that he will talk about. So this will be really exciting. Quickly about the process. So Sudhu will give the talk now, only clarifying questions, please. And then afterwards, we'll start with the committee members, external committee members first. And then, if necessary, we repeat second cycle through and then open to the audience, both on Zoom and in the room. And with that, would like to thank the committee for being here. So as I mentioned, Nancy and Shubham are actually on the internal committee members, and then Alberto and Mustafa from Meta, from FAIR, are the external committee members. Okay, looking forward to your talk.
Thanks, Michael. I'd like to start by thanking my committee, of course. They've been sort of my bouncing pad for ideas for the past 5 years, and it's been a great relationship I've had with all of them. And today my talk will be on spatial AI with vision and touch for robot manipulation. I can take any clarifying questions through the talk, and we can save like larger discussions for later. So the work featured is in collaboration with a lot of people across different institutions here, and they've been instrumental in sort of shaping the ideas of how this has gone and shaping the trajectory of my PhD by extension as well. I'll first begin by motivating a bit of my research. Robots have dominated manufacturing supply chains ever since the Industrial Revolution. And these are, of course, very complex environments requiring precision and coordination from robot manipulators. And there's a lot that needs to be desired from these environments. However, these problems benefit from some sort of structure. You have precise world models of what you're working with. You have synchronization between multiple robots. And at times, you even have teleoperation in these scenarios. And these are typically more of a narrow and repetitive goal that is pre-programmed with perfect observability of what the environment is. Rather than these complex supply chains, paradoxically, the largest leap that we're yet to make is for robots to operate in our own homes. And this is because household robots are beholden to unknown environments where they must achieve these complex, arbitrarily defined tasks without human supervision. The simple act of grasping for and stowing a given mug is a delicate dance between different robot subsystems. And this is what you would call an unstructured environment with more general purpose robots. And that's kind of the avenue of what this perception talk will be about. When faced with a given task, such as grasping and stowing a mug, there are different challenges. You can simplistically divide them into perception, planning, and control, and these subsystems talk to each other at times. Perception, or what we infer about these objects that we work with, can broadly encompass geometry. So reasoning about the pose of these objects, the shape of the manipulants that you're working with. They can also be semantic. So is this a mug, or is this a plate, or what can we do with that information? And the third is latent perception, which is, can you figure out textures and inertial properties and thermal properties of all these objects? With all of this information that you can get from perception, a planner will typically chart out a high-level task plan, so maybe a pre-grasp, a grasp, and some sort of non-prehensile action that you can get. And it can also optimize in configuration space about how you'd go about this task. The last part is the low-level control, which is looking at the nuts and bolts of the problem. So it's making and breaking contact, trying to exert external force, and reasoning between sticking and sliding regimes of contact. So each of these is a subfield in its own and a thesis of its own. And in this talk, we'll focus on geometric perception, or SLAM in this case. So the information about geometry here can give a planner and a controller very actionable information. And this can reveal certain affordances about objects, such as grasping a mug by its handle, for example. When we look at the specific task of geometric perception, it's crucial for robots to understand how they're manipulating with objects and how it responds to these actions that you take. And there's been a lot of great work that highlights how much can be achieved by explicitly defining what the object's representation and object's pose is. And this ranges from tasks in dexterity to bimanual manipulation to insertion. So there's a range of different downstream tasks that you can achieve with this perceptual output. For in-hand manipulation, the status quo relies heavily on visual methods, or circumvents these problems entirely via fiducial tracking. And this confines us to instrumented workspaces and expensive robot cages. So moreover, with vision, what we're doing is simply tolerating all of these interactions rather than embracing it in the first place. Additionally, a lot of these methods rely on you having some sort of CAD models of what these objects are. And we don't really have many of these luxuries when we're just deploying robots general purpose, such as in your kitchen. In such situations, there's always self-occlusion and environmental occlusion, and visual noise and distortion are very common in all of these. So it's not to say that you cannot achieve these through vision, but you are bottlenecked beyond a point. And this is evident from a lot of, when you do dexterous manipulation, you're trying to co-design where you're placing these cameras. And even with all of this co-design, there's still some edge cases in terms of places where you see issues in this. And spiritually, evidently, this is at odds with what manipulation really is, because we aren't really averse to contact. The community, this audience included, isn't just doing picking and placing. They're sliding, they're bumping, they're pushing, they're gating, they're reorienting different objects. And there's a lot of perceptual signal there that we are neglecting. So along with all of these different challenges, there are a lot of opportunities that we can embrace and try to fold into this problem. So the first being the sense of touch. So it gives us a great window into these local interactions that's woefully underutilized right now. Affordable commercial vision-based touch sensors can give us high detail information of these interactions. For example, a digit or a gel site sensor has become accessible to the price point of having the commercial and research community widely adopted. For a quick primer on how these sensors work, it consists of a gel pad that is a tricolor illuminated gel pad, and each of these sensors has a small perspective camera inside. When we make contact with an object, the elastomer of this gel pad deforms, and this comes out as an image that you can see, and a standard RGB image that can be published in, say, 30 to 60 hertz. With a learned model, we can go from these images to depth maps, for example, and we can do even more. So the focus of this talk, however, is going from images to depth and images to point clouds and seeing what we can reason about that depth information that we get. A secondary big advancement that we've seen is realistic tactile simulation. And this allows us to learn these measurement models for these sensors. So if I want to learn an image to depth network, simulation gives you the breadth and diversity and scale of interaction that is unavailable in real world robotics. And it allows you to augment and ablate all of these very well. And this enables us to transfer a lot of these observation models trained in simulation to the real world. The last part is online learning, which with growth in compute we can even get these things to run real time. With architectures such as NeuralFeels, they've shown great promise in computer vision tasks, such as shape estimation or pose estimation. And practitioners have been able to create high-quality 3D assets from just using camera images or RGBD information. And in this thesis, we try to look at the online learning paradigm, but adopt it for multimodal visual-tactile data. So for a quick overview of what this thesis is about, the succinct research statement here is that can we learn object shape and pose online from multimodal robot interaction? This thesis will bridge across different domains towards a multimodal perception stack. So taking ideas from manipulation, perception, SLAM, and tactile sensing. And indeed, the thesis statement is the setup of a standard SLAM problem in mobile robots, but it is for this object-centric dynamic task that we're handling. We operate under the constraints that robots in the wild would. So we have causal perception, so no access to future information. We lack fiducials or sophisticated motion capture. We have noisy, occluded multimodal sensing, and we're faced with these novel objects in the real world. The trajectory of my research has started out from simpler 2D problems, such as tabletop pushing, and over time to more complex dexterous interactions and how perception plays a part in trying to estimate and reason about these objects. Our first look into this was the planar pushing problem using force torque sensing. So we chose this given the physics of planar pushing is more well understood, and it's a great constraint that you can use in optimization. With these constraints and with touch sensing, we can demonstrate SLAM with an online optimizer, and this serves as a proof of concept for the eventual 3D SLAM problem that we wanted to solve. Following this, we looked at more of an online learning paradigm of using visual-tactile information to predict the shape of objects given a known pose. And this was my first introduction to working with visual-tactile sensing. We then dug deeper into tactile representations and what this can tell you about known objects that you interact with. And this was an interesting combination of learning and a more conventional particle filtering framework. So we can capture distributions of poses when a finger interacts with an object. And finally, we looked at the full SLAM problem, combining vision, touch, and proprioception on a multi-finger hand towards trying to get object shape and pose for in-hand rotation problems. Our work, each building on top of each other, can neatly fit in different parts of this Venn diagram. So anything that's shape reconstruction assumes that you know the pose of these objects. Pose estimation tasks assume you have a CAD model of these objects. And down the middle is where you don't really have any assumptions of the objects that you're working with, which is typically the hardest regime to work with. We'll use this Venn diagram to further understand how prior work has evolved over the past 2 decades. So initial work in shape reconstruction considered discrete touch sensing and more implicit surface representations to try to reason about either force torque or binary on-off contact sensing. There was other work using visual tactile sensing from Bauza and others that supplant these methods with more accurate geometries for vision-based touch. Visual tactile fusion was also considered for batches of measurement to try to learn what the shape representations of these are. In the pose estimation problem, you assume that you have access to these CAD models. So initial methods focused on simpler setups. So particle filtering over discrete contacts for simple operations. And over time, fusing this discrete contact with visual sensing for more tabletop manipulation problems. And finally, with dense touch, you can get richer localization signal that is pushing the boundary for working with more planar pushing problems, as well as small part manipulation, where accuracy is key. Down the middle, we have methods such as Moll and Erdmann, who considered the initial version of this problem with a smooth convex object between 2 planar palms. This was later demonstrated as a batch SLAM problem with force torque sensing by you and others. And other work looked at achieving SLAM through touch with specific constraints on the object's motion. So either using a roller gripper or doing small patch manipulations. And finally, closest to our work is work like finger SLAM, which uses a single touch sensor and an unobstructed camera, which is still a step down from what multi-finger general dexterous manipulation would be like. So as an overview for what this talk will be about, first I'll talk about an in-hand SLAM system. So it's the NeuralFeels system that fuses vision, touch, and proprioception to get object models. And the second part will dive a bit deeper into how tactile representations play a part in an eventual perception stack for these. So first I'll dig into what NeuralFeels is about. We hand the robot an unknown object that it hasn't seen before, and through a combination of vision, touch, and proprioception, so joint encoders in these cases, we would want to figure out both the pose of the object over time, as well as evolving shape of this. So this is a poorly constrained problem, as you can see, but we try to leverage all the constraints we have to us and maximize the information that we can get from sensing. In these results, active perception is currently out of the scope. So all of these are policies that we train beforehand and we execute to collect data. And I'll talk more about perception-driven policies in the future work that we have. So to give you a teaser of what this looks like, we can visualize the input, which is visual and tactile data that we see. So we have an RGBD camera looking at the scene, as well as 4 tactile sensors mounted. The outputs of these, which I'll talk about later, is trying to take segmented depth information from both the visual camera as well as contact patches from the tactile sensing. And the last part is visualizing both the online rendered surface, and this is just taking the SDF of the object and running marching cubes on it and showing this reconstruction with respect to what the ground truth is. So I'll let this video play out to explain the whole thing. So here we hand the robot this bell pepper shaped object and try to visualize the gradual reconstructions and the robust tracking of the object over time. As mentioned, our manipulation policy here is pre-trained. So we carry out this policy that only uses joint encoder information over time to predict its next action. The object model over here is initialized using the first visual frame. And over time, we complete this with the visual and tactile information that we get. We see a similar result from simulation here, where we have this rubber duck object. The rotating visualization on the top right shows how these reconstructions compare to what the ground truth of the object is. And we also overlay the track pose of the object here with the rendered normal visualization to just show you how the pose is changing over time. Similar to a classical SLAM system, we chose to divide this into a distinct front-end and back-end optimizer. So the role of the front-end is to derive object-specific information from raw multimodal streams. And these models are all pre-trained. The back-end uses the front-end information. So in this case, the visual tactile depth information, and reasons about the object's shape and pose over time. And this is an online optimizer that we're running. So to first dive into how we process RGBD information with our front end. So our goal here is to kind of singulate what the object is with respect to the RGBD information, because there's a lot of information that if we incorporate, such as the dynamics of the rotation of the fingers and the background, that we do not need. So here we use the segment anything module to singulate what the object is using what we call as embodied prompts. So the first one is, if we can use kinematics, we can try to ignore where the fingers are. So that serves as a negative prompt to this. If we assume that the object is always in hand, we can give the centroid as a positive prompt for where the object could be. And once we have some sense of the estimated shape, we can also reason about occlusions. So if you find that something's occluded in terms of a finger, we can ignore that as a prompt. So using these point prompts, as well as a history of mask information over time, we can accurately singulate the object depth without many false positives. And there's some other examples over here. One of the surprising outcomes of this research is the realization that this simple combination of kinematics and a foundation model can give us such good performance. And this is not initially what we sought out to do, but the growth in foundation models over time just sort of pushed us in this direction. Now, once we have segmented RGBD information, we're looking at the next problem, which is trying to get these contact patches from a touch sensor. So here we train a monocular depth network, a vision transformer, to predict both the contact measurements and identify contact versus non-contact geometries. And this is entirely trained in simulation. And we see that it can generalize well to sensors across the hand. So we have 4 different sensors, and it works well for these sim-to-real kind of problems. And this gives us essentially depth information from the RGBD sensor and from the tactile sensors, and we can kind of fuse this into a cohesive model. So to train this tactile transformer that we call it, we take a large selection of objects from the YCB dataset that we can interact with. And once we have this large selection of objects, we densely sample each object for a bunch of different contact poses that we can simulate tactile information from. So we can use Tacto or any other open source simulator for this. And once we have those resultant tactile images, as well as the depth maps that we get from them, because this is simulation, we have ground truth depth maps. We have this paired information that we can use to train a supervised model. Once we have these paired supervised information, we then feed this into a vision transformer network that, when supervised with a reconstruction loss, can give us something that transfers well across different sensors. And what we figured out over time is the sim-to-real transfer is not directly obvious or something that just works out of the box. So in those cases, we looked at different ways of augmenting. So the first one we looked at was sensor augmentation. So here, when we collect information from Tacto, we can essentially supervise it with different signals from a real sensor. So we take 25 different digit sensors, so just try to brute force it, and we get all those templates, and we try to augment with that information. The next is lighting randomization, so we can vary the RGB information in simulation. We have pose and pixel noise that we can apply to all of these samples. And the last one is standard warp and image transforms that you can use. So with all of this, we can get a transformer network that works pretty well for going from images to contact patches. So both the depth information and where you make contact with the sensors. Armed with this visuotactile depth information, now we pass this on to the backend, which is the shape and pose optimization part. So here we'll talk a bit about how we represent these objects. So we represent these as SDFs, or signed distance fields. So we have a defined volume. So if you say you have a cube in hand, we have a defined maximum volume that an object can be. And the initial pose of what this SDF is always centered between the fingers of this object. To supervise the training of this SDF, we can sample depth information along different cameras. And this is something that methods, neural methods like NeuralFeels and all of those do very well in terms of ray projections and sampling the actual volume to get depth information. So assuming we have these perspective cameras, since we can also have perspective camera models for the tactile sensors in simulation, we can do the same. We can then take all of these frames or keyframes that you get and periodically add them into a set that we can use for batch optimization later. With these samples, we want to run an alternating optimization. So we want to both build out the shape of what the objects are, and we also want to refine what the poses of the objects are under motion that we get from manipulation. And at each time step, the SDF part is governed by an instant NGP network, which is essentially taking coordinates, so XYZ information, taking it to a high dimensional state space, and also trying to regress that to a single signed distance, so distance from the surface value. And with this information, we can build out what the SDF is of the object over time. And if you run something like marching cubes, and if you color it appropriately, we can get outputs like this over time. But that's not enough, because these are dynamic scenarios where the object is moving over time. So we also have, as the object is manipulated, we maintain a pose graph of what is happening to this. So the base pose of this SDF, essentially. So here we govern it with this SDF loss, which is the same loss, but that we apply for learning the shape of it, but instead we use it on the SE3 pose of what the object is. So to sort of visualize that, what this SDF loss is doing is taking the simple example of, if you have this cube in hand, you have segmented depth information, and if you initialize your assumption of what the state of the cube is to be far away, what it's trying to do right now is attempting to pull it towards what the ground truth depth information is by sampling in this volume. So any prediction over here that initially starts out has a large basin of attraction when we use visual sensing, which essentially tells you that we get global scope from what we get from vision. We can get the same, but more precise information that we get from tactile sensing. So here we can, because we model the tactile sensors in a similar fashion, we can get this alignment of more smaller features here, such as the ridges of what the cube is. So essentially things that vision doesn't get you. And since we model all of them as cameras, we can afford to do this for all of the sensors we have. In addition to this SDF loss for pose, we also have a pose regularizer, which essentially tells you that between two time steps, we want to keep the pose of the object somewhat well-defined and well-behaved. And the last is an additional constraint on frame-to-frame ICP using the visual tactile point clouds that we can get. So all of this, while the shape optimizer is using like a first-order gradient descent method, the pose optimizer is using Thesis, which has a second-order Levenberg-Marquardt solver underneath. And the idea is we alternate between these two to get a good alignment between what the shape and pose of the object is. Through this simultaneous optimization, we can start out from scratch or with a first visual frame, and over time we can iron out what the shape and pose of the object is to align well with what the ground truth tells us. To evaluate this perception pipeline, we would first like to collect some interesting in-hand rotation data because we chose in-hand manipulation as a task. We use an algorithm based on rapid motor adaptation. So it trains in simulation to rotate canonical objects in Isaac Gym. And it simply uses a history of joint encoder information. So to predict the next control action, it sees how the state is responding to the dynamics of the current object. And we can directly deploy this to a large set of real-world objects, as long as the scale of the objects are somewhat similar to what we had in training. And this is a means to collect interesting visuotactile data that we can essentially store as data sets and use to evaluate our perception methods. With this policy on hand, we can collect these. We have 70 different experiments all across the real world and simulation. For getting ground truth information, we have 3 different cameras that are tracking the objects. So we run a 3-camera tracker in the real world to get ground truth pose. And in simulation, it's easier because we have all of this privileged information on hand. But each of these manipulation instances is a 30-second sequence, and we collect and log all of that for more large-scale testing and evaluation. So when we come to the results, the first thing that we wanted to look at is what the benefits of this multimodal sensing is for enhanced SLAM, or does vision and touch actually improve what we get? Qualitatively, here are some other results from the SLAM experiments with the overlaid rendered normals, both in the simulation and real-world experiments. The experiments in the real world are definitely more dynamic as compared to what the simulation gives us. So that was definitely a challenge in terms of sim to real transfer. But with no prior models or motion constraints, these are conventionally hard problems. But our pipeline can both track and build these object models over time to a good degree. When we take the final outputs of a lot of these runs and we run marching cubes on them and color them appropriately, we can get these SDFs and these meshes that we can compare to. And from a qualitative standpoint, we can observe that incorporating touch information helps in 2 different ways. One is in terms of shape completion. So regions of the object that are occluded can get sort of figured out via touch sensing. And the other one is more of shape refinement. So if we have more local information, we can try to incorporate that to reinforce what we get from vision to get smoother surfaces, flatter surfaces, and things like those. So when we look quantitatively, we can see that incorporating touch gives us better reconstruction accuracies compared to vision only. And in all of these, so in the shape metrics, the higher the number, the better. This represents an F-score metric, which is a common consensus amongst multi-view and 3D reconstruction problems to use the F-score. We also see corresponding trends in pose estimation, which in these cases, lower the better. And because it's kind of a chicken and egg problem, you can assume that a large shape metric is correlated to a low pose metric in most cases. And these trends broadly align between the simulation and real world experiments that we get. But obviously, there are some offsets. And at the last point, if we define an arbitrary number saying 1 centimeter of pose drift tells us that the tracking is a failure, we see that when we incorporate vision and touch, we can get lesser of those instances of failures in tracking, which really bolsters the point of using multimodal data rather than just a single source. For concrete numbers, we can show these average shape and pose errors. So I have scores of 81%, pose drifts of about 4 millimeters. And we can actually do better when we assume that we have the CAD models of these objects. So in these cases, we're simply freezing what we get from the SDF network, and we're reducing the pose errors by half, essentially, to around 2 millimeters of accuracy with respect to what the ground truth gives us. And these are common scenarios for more industrial and factory automation tasks. So where you might have like a McMaster CAD model to work with. And the way you think about it is freezing the SDF network and just simply running the pose optimization alone over time. So this is, of course, a welcome byproduct of the whole SLAM system that we want to work with. And another interesting yet not very surprising result from this is that if we run this same tracking algorithm, but with only touch data, you do significantly worse in comparison to vision or vision to touch. And this sort of reinforces the idea that these measurements lack global context. There's been a lot of work that corroborates this in the past. And however, we see that when we combine these, we essentially get the best of both worlds from the modalities. The last thing we wanted to look at was all of these results so far were predicated on having these ideal camera configurations achieved by this co-design of the problem. However, in many manipulation problems, these are far from ideal due to self-occlusion and environmental occlusion. So let's see how our tracking algorithms work there. So in these experiments, for example, we take a given in-hand manipulation problem, and then we simulate 200 different instances of this problem with different cameras as looking around the object. And we run both our visual and visual tactile estimators in these cases, and we try to compare the relative performances of both of them. So here we color map the performances. So 0 means there's really no improvement in using touch, and 20 millimeters means there's a huge improvement in using what touch sensing gives us. And what we can observe here is that when we have regimes that are low occlusion, so things atop the camera, for example, or things with favorable camera views, we do get improvements, but this is more of a refinement over time. And the place that we really make our money is when we have high occlusion regimes, so things that are directly below the camera, which gives us more 60 or 70% of improvement when we incorporate this touch sensing. And we can solidify this by charting this out in terms of occlusion scores that we define. For example, something atop the camera has a score of 0 because you have perfect visibility. Something below the camera, you literally do not see the object at all. So that has a score of 1. And we can see that these trends usually correlate here, giving vision and touch a superior error here. And this drives home the point that touch at the very least can refine these estimates, and at the very best disambiguates all of these visual estimates during in-hand manipulation. This whole ablation serves as a proxy for these in-hand manipulation tasks where there's visual occlusion. When we have a fixed point of view camera or a wrist-mounted camera, we're bound to encounter a fraction of these scenarios where there are these high occlusion regimes. And as we can see, it also doesn't hurt to have this in more fair weather scenarios because we can at least refine the estimates that we get. So to summarize this work, it's just really scratching the surface of what we can get through a combination of multimodal sensing and online learning. So we can get all of these shape models and track these over time with really no priors on what the objects are. We can robustly track and reconstruct these novel objects. The system doubles up to track these known geometries if you give it a CAD model. And the tracker can make the best out of occluded scenarios over what visual methods give us. We've also experimented with a full system on these robot cells and are working towards open sourcing these ideas. The multimodal data set would be also beneficial to those who want to work on more robot learning problems. If you want good annotated visual tactile data, you can try to use these as an avenue to do that. Now that we've covered more of an enhanced SLAM problem, I also want to dive a bit deeper into tactile representations and how it can be beneficial to a localization task. So here I'll talk a bit about MidasTouch, which is a previous work to this. So in this task, we're not just looking at a full SLAM problem, but rather a finger object localization problem from touch. Here we assume that we know that we have models of these objects, and we're interested more of in a representation for the touch sensing that can give us a distribution of these poses. And this is vital in many cases where just a single estimate of what these poses are might be insufficient. So if you have symmetric objects, you want to capture, say, all of the antipodal distributions of what you think the pose is. And succinctly, what we want to do is, given a stream of this pose tactile data, like the one on the left, the one on the right, can we figure out where we are on the surface of the object? So this is essentially like a Where's Waldo problem, but for a robot finger on an object. At a high level, what MidasTouch can do is it extracts 3D surface geometries from tactile sensing. It can summarize these into these learned representations. And we can use it to disambiguate over time with a particle filter, where you think the pose of the object is. For a sneak peek into what the system can achieve, consider the case of me over here trying to slide this robot finger across a different object. We have the ground truth of where the sensor is. We have pose particles distributed about the object. We have a likelihood at each time step that tells us the embeddings are telling us where it thinks the sensor is. And we have images, and we can have 3D information that we derive from these images. We really start out with little to no information of where we are over time, but the moment we hit salient features, such as corners or edges, we can quickly localize onto a set of distributions that can explain that. And the inputs to this is just tactile images and noisy sensor poses that you can get from kinematics. We see that we have a heat map as well as a pose distribution that we refine with a particle filter. And this charts out really the pose errors over time that we get from all of these manipulation sequences. So our goal with a tactile representation here is that similar geometric shapes should map to similar latent embeddings, or they should have a high cosine similarity score. And for example, if we have this given mug over here, you would like to, if you trace out the lip of the mug, you would like to have embeddings that are similar, but they should be very disparate from when you make contact with the flat patches of the mug, for example. So essentially trying to give a haptic apprehension of what the objects are and try to integrate that over time. So how do we go about getting these embeddings really? So the key insight here is that place recognition modules have existed in mobile robotics for a long time. So we don't really have to search too far. For problems like loop closure, there have been ways to take point clouds, condense them to embeddings, and try to compare them to figure out where you are in a given scene. And these have a pretty good generalization and can be trained with large-scale data using contrastive learning methods, for example. And these point clouds, if you think about it really, or if you squint enough, they're really larger scale point clouds that you would get from a tactile sensor. The key insight here is there's a lot of commonalities between what you might think as very disparate sensor domains. Since we're operating with point clouds and depth information, we can essentially take these, fine-tune these pre-trained models that we get from data and use the same tactile simulation method that I talked about in NeuralFeels. So we take a bunch of different objects, we simulate different contacts on them, and use it to fine-tune these pre-trained models that we have. So what we get from this is a method to really differentiate, again, between what the edges are versus what are the flat surfaces of a mug, for example. And the idea here is not to be precise. You don't want, because these are very symmetric objects, there's a lot of ambiguous information, because when you make contact with the lip of the mug, you don't really know where you are in the circumference. The idea here is to get some good signal and then use a non-parametric filter to sort of weed through that signal that we get over time. So to visualize how these representations look, here we take all of these different objects, we subsample a lot of poses, and then we try to essentially build a TSNE color map for the embeddings. So the idea here is things with a similar hue usually correlate to things with similar tactile geometries that you can get, so different edges. So with this information, we see that we can delineate a lot of information, such as the edges of the sugar box. We can get the ridges of this power drill, the sort of edges of the scissors, as well as even the threads of the baseball over here, which are delineated in similar colors, which goes to tell you that they have similar embedding scores. So this is definitely a useful signal that we can integrate over time. So now that we have a way to generate these tactile codes, we have an image, we feed it through this network that uses the 3D information, and we get these tactile codes. Like I showed you before, we have these known object models. So we can quickly generate a code book, per se, of subsampling this object, getting different embeddings, and storing them. For a given localization task, if you have a measurement at time step t, you can derive that tactile code, and you can quickly compare it against what the codebook gives you. So if it has a very high cosine similarity, we would take that as a likelihood score. And this likelihood score goes straight into what we have, which is a very conventional particle filter framework. So it uses a learned measurement model, but the downstream output of this is really just SE3 particles on the manifold of what the object is over time. And from practice, we can see this running downstream at around 20 hertz or so. So we can get this to parallelize and run pretty well. To evaluate all of these, we collect this huge data set called YCB slide, which has me interacting with all of these objects with ground truth motion capture as well to get us both the sensor and the object's pose at each time. So this data set has also found a lot of adoption in the community because it's one of those that has good pose annotation for tactile information that we can work with. So here's another example of the filtering framework in action. So just as before, we have me sliding across these objects. And for the sugar box, for example, we see that you roughly have a convergent behavior when you encounter an edge of an object or a corner of an object. And we really have a lack of information when we go on flat surfaces, which goes to tell you how featureless this object is, but we can still do pretty well. For a more complex objects, such as this power drill here in simulation, we can localize much quicker because we have much more signal to work with. And upon convergence, this becomes more of a local tracking problem. So it's a much easier ask for a particle filter to do. Probably the most interesting one is capturing these multimodal distributions. And in these cases, two different antipodal poses is what I'm representing. So for a perfectly symmetric object, we can capture two trajectories that equally explain away the information that we get. So even though you might have high poser, I tend to think of this as a feature rather than a bug of this method. So we believe that capturing these symmetries is helpful because when you scale this up from one sensor to 4 sensors and you have a dexterous interaction, you'd want to reason about all of the different sides of a cube that you can orient it, for example, which a distribution can actually capture. I'll end with some thoughts about research directions that I'm super excited about and what this line of work opens up to. So broadly, with NeuralFeels, we found that spatial intelligence can really drive further what you can get from general dexterity. And the hope is that future work can kind of latch onto this as a perception pipeline for what they want to do. So this can broaden the capabilities of what robots can do in these environments without having expensive motion cages or instrumented setups. And really the key or the takeaway from this is to maximize the best information that you can get. So try to encompass all the modalities you have and try to think about more resilient ways to process this. So have robust backend solvers to work with that. While the sensing and hardware may change over time, the key that tactile perception and simulation will be vital tools is something that I believe on. And if you want to learn more intimate knowledge of interaction with these objects, this is something that we should really harness going forward. And there's been a lot of interesting work in developing better simulators, differentiable simulators, as well as working with better tactile sensors. And I've sort of done my PhD in this regime where both of these fields are evolving at the same time. So it's hard to actually keep track. But I think beyond a point, we will come to a point where we attain a stasis with terms of what sensors we're working with, and then we can try to build our algorithms over time. So for some interesting future directions, the first one is what I swept under the rug in the beginning, which is using perception for action. So we've been working towards integrating perception solutions for better policies. And this is work that I did with Housie and others, which for starters looked at taking the same visual and tactile information, but instead combining that into this implicit representation of embeddings. And we found that using these really informed and improved these reinforcement learning policies that we can get. We're still plagued by this sim to real gap, for example. If you change the viewpoint of the camera drastically, you might have out of domain, out of distribution information, and you can't really diagnose what's wrong there. So one thing that we'd like to focus on in future work is, can we actually get the best of both worlds and try to ground all of these policies with more spatial representations? So it doesn't have to be explicit object pose and shape, but pipelines such as NeuralFeels do enable that to happen. A second avenue here is really the alternate of an explicit representation. So I chose a direction in my research where you have explicit SE3 poses of these objects. We have a representation of these objects, such as STFs, but there's an alternate school of thought that tries to learn spatial maps directly on pixels. And this also gives you some diagnosability in terms of what is happening. So it's not completely end-to-end, for example. And this can also be leveraged for these simple manipulation tasks. In many cases, with recent foundation models like Dino, you don't even need to fine-tune these. They can just work out of the box. So that's why it's a very interesting direction to feel. The last one here is, so really the benefit of a neural field or any coordinate network is the ability to extend just beyond appearance and geometry. So indeed, there's been a lot of work that tries to use these online learning mechanisms to predict texture, to predict friction, things that you can't really see with vision. And that's really where I think expanding the state space of what these objects are gives us the biggest gains. So if I look at a hammer, for example, I can't figure out that it has a disproportionate mass distribution, but interaction can unlock that. And there's a huge role that physics and tactile simulation can play here down the line. That brings me to the end of my talk, but I'll also like to end a few minutes with some acknowledgements here. So first, a big thanks to my committee. They've been in constant contact with me for the past 4 to 5 years, however long I've been in my PhD program, and they've been enabling and only supporting me through the whole thing. So thanks to Shubham for all these guiding large questions and helping me zoom out on what the larger picture is. Thanks to Nancy, who Michael and I have been chatting with since the start of our PhD. She really wanted to be here in person, but we were unable to work out a time for that, so sorry about that. During my first year in the pandemic, I just cold emailed Alberto once about collaborating on this planar slam problem. And to my surprise, he was very enthusiastic about it. Over the years, I've gotten to like bounce a lot of ideas off of him, and I've gotten to know students and I've learned a lot from them. Mustafa has really been almost my second advisor to me over the latter half of my PhD. And I've learned a lot working with him and the team at Meta. It's not just the theoretical discussions, system design, but also how to like better present and spotlight your work. And a huge thanks to, of course, Michael, who has been supervising me through my master's and my PhD here at CMU. He's given me, as he talked about, he's given me a lot of freedom to explore ideas, not worry about funding and all of those things, and really forge collaborations and solve these large theoretical problems. It really does take a village to write a dissertation, and I would have to acknowledge a lot of people here. The past and present of the robot perception lab. The lab is really forged in the spirit that no matter what domain and what robot you're working with, the underlying optimization problem is really the same. The folks from the Meta Embodied AI group who I've had the privilege of working with for the past 2 years. A lot of what I presented today would not be possible without them. The RoboTouch and the MCube Lab for building wonderful collaborations, especially in the initial years of my PhD. The Field Robotics Center, who I've been working with through my internship at CMU and my master's program and all of those. And finally, the larger CMU community, some of whom are the reason I got here in the first place, some of whom are springboard for ideas that I have, and some of those who have been just constant supports through the years. As Michael talked about, I've been at CMU for a while. So the RI has been a wonderful long journey for me. I came here in 2016 in the RISS program where I worked with Red Whittaker on lunar rovers and kinematic state estimation. Over time, I joined Michael's lab in 2017, where I spent some time working on underwater progress. So looking through the water, trying to localize, trying to do active exploration things. And when I started my PhD, we delved more into perception for manipulation. And that's what this presentation was really all about. Pittsburgh has really treated me well over time. These are some snapshots of the robot perception lab over time. And one of them is during COVID. So that's that screenshot over there. Shout out to all of the friends who have come out with me. That's been an integral part of me being in Pittsburgh. The people I run with, the people I bike with, the people I ski with. I'm pretty fond with Frick Park. So watching the Fernallo Bridge fall down and come back up through the course of my PhD has been something. Yeah, and the broader support system has been good to me. People all through Pittsburgh, through the US, and back home in India as well. Finally, I'd like to thank my fiancée, Varsha, who's there at the back, for her undying support. And there's been a lot of ups and downs in research, and she's been with me through and through. And of course, my family. I'd like to thank my parents, my brother, and the extended family, because they've really put me in a privileged position where I can pursue what I love. With that, that brings me to the end of my talk. I'm happy to take any questions. Thank you.
Okay, so we'll start with the external committee members. I think Alberto, you're the furthest away, so if you have any questions.
Hello, can you hear me?
Yeah.
Awesome, nice.
Very loud, yeah.
Oh, sorry.
No, that's our fault.
There's not that many questions that I haven't asked you throughout the years. I think I've asked you many. Maybe something I was wondering, the computational load of running all of the things that you're running in your system. Can you give us a perspective on that? It's like how real time is, if it's not sufficient, how would you do it? What would you sacrifice?
Yeah, for sure. Yeah, we do have numbers on these things. I haven't added them to the presentation per se. So with NeuralFeels, for example, let me quickly pull up a slide that can sort of describe this as well. Oh, I stopped sharing my screen. Give me a second. Yeah. So for example, with NeuralFeels, the major compute bottleneck that we have right now is we're trying to do this online learning paradigm, but we want to do it real time. So what we found is we can, at the current state of what we have in terms of compute and fairly unoptimized code, we can get it to run at say 4 to 5 hertz if we're doing a SLAM problem. We can get it to run at say 10 hertz if we're doing a pose estimation problem. But what we really need to do is try to optimize that over time. So I think there are different ways to go about that. So you can do a different number of pose iterations versus a different number of map iterations. We're using very sort of high fidelity SDF models. So say 200 cube grids, but if we size those down, we can do faster. But a lot of the results here, we're just saying, let's take the best model we have. Let's try to run it ad hoc after the fact on a data set and see how good we can get. So we're still not there at real time, but I would say if you run a policy slow enough, you can get it to run.
So what about the question of how fast would you wish it would run, right? So I'm thinking like, you see these fitting a sort of mid-level policy that, I don't know, something that is streaming targets at 10 hertz, or something that is running, that is feeding back into a faster controller that would need to run at 100 hertz, or I don't know, 300 hertz. When would you be happy?
Yeah, I think, okay, so the first thing is you're sort of hard capped on when we take the perception and the planning pipeline, you can't really get perception to run to the speed of a 300 hertz controller, for example, because you're bottle capped at what the camera can give you in terms of 30 or 60 hertz, and the tactile sensor is at 30 or 60 hertz. So I would say that if you can get post predictions to the speed of 20 to 30 hertz, I think that can be sufficient. You can try to interpolate between them, but if you really want to go beyond that, I think we have to do something more interesting in terms of more, there's been a lot of work in like event-based tactile sensing, for example, that can give you really fast feedback. We can try to leverage force torque sensing and things like those that aren't just cameras anymore. So yeah, I think with the current model, I think if we have it fast enough to say 20 to 30 hertz, I think we can do something good with it.
And then what about computational size instead of time? Like, does this run in one computer, or do you need more than one computer to run it?
Yeah, right now, since at least the purview of my work was not to optimize for real time, it's just running on a single computer with either like, you can run it either with a 4090 or 3090 GPU. But theoretically, the correct thing would also be to split up the optimizations to try to do more of the shape optimization on one GPU, to do it's just bookkeeping at that point, and those are really the hard engineering problems that we'd want to solve. But distributing the workload is definitely something that would benefit this.
Cool, nice. And maybe one more question, and then we can take turns. Have you thought about extensions of the type of tasks that you're applying this sort of like shape tracking framework to, right? So it seems like right now you're thinking of like this rigid object for which there is a model that is sort of fixed over time, or that it converges to something over time. But like, what about like, I guess that the formable objects would be the naive question. But I'm thinking things like
an articulated object, for example, I guess, right?
Or even like I open a drawer and there's 25 objects. There's some rigidity to some aspects of it, but there's, I don't know, there's a mumble. The mumble is enough that it might be difficult to model it as a collection of rigid objects. Thought about extensions like that?
Yeah, I'm not sure. So this is really aimed towards a single object problem. So multiple objects, I think if you have semantic masks and you can try to attribute different objects, you could do that. With more deformable objects, where not deformable, but when you need to, like, you have a pile of objects and you need to singulate that information. I think we're really right now we're a bit hamstrung by the fact that we have this online learning module, and it's we only need to sample information from the past continuously to remember it. So I think unless we can reason about essentially the fourth dimension, so time, how things move over time, I think incorporating that, some sense of uncertainty for those, I think will be helpful. But I'm not I don't have an immediate idea on how this can extend to, say, a more deformable subset of objects.
Nice. happy to pass the baton to someone else.
Let's continue with Mustafa.
Hey, Sudhu. Great talk. And as always, I love the extra mile you go in making your visuals. Those are really great. I'll start with a question that's maybe offshooting from Alberto's question. So what do you imagine is kind of the next thing to do with these pipelines, the perception pipeline? So obviously pose and shape is kind of your main focus here. What do you imagine are kind of the next things to work on? Are those other properties? Are those things, still in the pose and shape regime, but sort of beyond pose and shape? And then, would your current perception pipeline sort of extend to those, or what changes would you make to that?
Yeah, so yeah, I think there are two questions here. The first is, I guess, how this, the natural extension for that work, for example, is just taking a stream of pose information, a stream of evolving shape information, and try to encode that into some sort of policy that we can work with. So I can think of a naive way of doing that, which is not taking, for example, like what I showed you in terms of how these work, which is taking visual information as well as tactile information and encoding that. You could instead take your current prediction of shape and pose, feed that through PointNet or something like that, and try to get a better embedding from that. That could be one way of trying to use the explicit information. And the second question in terms of using more latent information, I would think of it more from like, if you think of it from like the nerve perspective of, you don't just have color information, you also have viewpoint variance. So they essentially have extra terms tacked on to the optimization. So I think the biggest challenge there is trying to get, essentially trying to figure out what the supervision for this problem is. So do we want to go about like a self-supervised route of, if we're thinking about texture, if these materials are the same, can we try to supervise with that information? Or do we want to go in terms of like a data set route of collecting all of this large scale interaction, somehow annotating that information? Or the last one is, do we want to go entirely in simulation where we have perfect information and then think about transferring this to the real data? So for me, geometry was more easy to envision for these. So that's why I think it was easier to sort of build out the pipeline. But when we think about texture and inertial properties and all of those, it's a bit more vacuous, I think. Yeah.
That makes sense. My reasoning is, you're sort of in geometry world right now where touch is more complementary, and once you get sort of beyond that, in forces and things like that, there are only so many things you can do with vision. So I guess, yeah, your line of reasoning makes sense.
So yeah, so the way I think about it, it really becomes from a multi-modal problem, I think it becomes a cross-modal problem in those cases, because there you can really use your interaction information to actually learn better about what you're visually seeing. So a very common example is transparent or reflective objects, which we can't really use in the current pipeline because we don't have depth uncertainty information. So visual estimates will tell you that this is a transparent mug, but you could essentially be finding a point that is like way beyond that. But if we have touch information, we can instead try to incorporate that in a cross-modal way. And that's, I think, the shift in the paradigm that we have to make there.
All right. And my other question for now would be, so you've been working with the vision-based touch sensors for a while now. What do you think? Are we good there? Do we need anything more in these sensors? Are we bottlenecked by the hardware, or are we bottlenecked by the algorithms?
I would say hardware, yes. The first is really generalization. That's one of the biggest pain points, I think, of the whole research is, since I chose this whole sim to real domain, it's really hard to get things to work out well across different sensors. You don't just get a calibrated real sense that you can work with. For example, for a tactile sensor, you have to either collect some data and try to get it to work for that. And then the moment you switch to a different sensor, that doesn't work out. So I think these things, with a nascent field, I think these will standardize over time. The other is like I talked about, I think is just the frequency at which we get the data. So if we're going to do more interesting control tasks with tactile sensing, we might want to more focus on high frequency information that vision-based tactile sensing can currently not get you.
Okay, thanks, Sudhu. I'll pass it to the next committee member for now.
Okay, so let's continue with Nancy.
All right. Well, thank you for the wonderful talk. I think this work is very, very interesting. Excited to see these results. I wanted to ask you about, so I think there's this underlying assumption here that more information is better. Like, so if we have a better reconstruction or a better estimate of pose, that's always what you want. And I think, you know, since you're mostly thinking about the reconstruction problem kind of in isolation and not so much considering the action part of it yet, I think that's fine. But as you start to think about actions, I think that there's this question of, well, maybe you don't need to reconstruct the whole object geometry, and maybe you want to think about what signals are most important and how to get them quickly. And I wonder if you have some thoughts about that. I think I'll start with that and then follow up.
Yeah. So one thing that I think would fit right into this, and we haven't really explored in this topic, is really trying to get priors for objects. So the ideal scenario really is don't have this whole online learning paradigm, but you have this 1 or 2 frames of this object, and you want to if you have 2 frames and you think it's a mug, you try to predict what a mug looks like and then work with that. So I think the first major push that we would like to do in that direction is try to incorporate priors. So each time I hand the robot a mug, like it's probably interacted with thousands of mugs over time. So if we can essentially codify what that is in terms of shape and bootstrap the whole problem with an initialization of that, I think that should do pretty well for a lot of manipulation tasks. The only issue is when we get wrong, I think we get that it turns out really bad. So if we predict the handle to be somewhere else, that's not a good sign. So I think I like representing things spatially because it's more diagnosable. You can see where things go wrong. But I also agree that there should be more experiential knowledge that we can bake in. And I think that's the first thing we would need to get the minimal subset of information that we want to work with for manipulation tasks.
So just to push on that a little bit more, so some of the things I'm thinking about in terms of actionable data are, I just want to pick something up, or I want to make sure the tip of the tool is oriented the right way, and I don't care so much about the other details, or I want to make sure that I'm grasping the object securely, and that's all I want to know, or more securely. These kinds of things. So just as a kind of anecdote to fill that out, some time ago we did some human subjects experiments where people they knew what object they were picking up, but they could not see it, so they were blind. It was blind grasping, and they would most people, we didn't tell people what to do, but most of them would adopt this kind of tapping behavior where they would tap around till they felt it, and after about 1 tap they would have enough information to pick the thing up. So that's the kind of thing that I'm thinking about.
Yeah. So
yeah.
So it's more of like a haptic apprehension problem in those cases. So
yeah, I just want to think about have you think about what if what's the minimum you need to take an action, and how do you think about some of these problems if you have only the action in mind? And one of the things that we would use it for instance, would be in thinking about, well, I want to figure out where to put my sensing on the robot hand. Where should I put it? Right? Like these robots that you're working with, they have really great fingertip sensing, and maybe it would be great to have the same high resolution sensing all over the robot hand, but maybe we don't need it, and maybe it's too slow anyways right now. And so maybe we want something else. So I just wanted to open up that question and see if you had some thoughts about that.
Yeah, so this operates right now in the regime of fingertip manipulation. So we have essentially things on the palm, things on the along the sides of the distal ends of the sensor are really, and if you can see, like, we've oriented the sensors such that we can always get those contacts. So I think the next real step is to, like, when I talk about this deluge of information, I think where can we get better? So for example, grasping with the palm of the hand will most certainly be occluded for vision and will most certainly not give you fingertip sensing. So that's where either taxels or things like reskin, more sort of less resolution, but more sort of distribution of surface area, I think would be helpful. The way it sort of combines with this like camera first pipeline is a bit more unclear, but I think if we can incorporate essentially continuous signal with discrete signal, that would be pretty good for us.
Okay, I think I'll pass it along with that. Thank you.
Yeah, first of all, I think great body of work, really impressive talk. Some questions on the second work. So you showed these nice results of, let's say, the TSNE with your learned embeddings. So first of all, those embeddings were learned for that object, right? Or sort of fine-tuned for that object.
Yeah, so that's a good question, which I didn't clarify on. So it's actually not object specific. So it's actually just geometry. But when we run our filter, we essentially pre-generate all of this information. So the reason we pre-generate the information is when we're running a particle filter, we have, say, 10,000 different particles. So if we want to query where you think something is, you'd have to essentially run a query 10,000 times on the surface. So we instead do that because we have the object models. We just use the model, which is the same for all of the objects. We get the embeddings, and then we just store those. So then it becomes like an SE3 lookup rather than a full query. So yeah, to clarify, it's a single model for everything. It's based on geometry and not object.
So on that note, I was just wondering how much benefit you get from learning this model using the kind of objectives you described versus, lots of other naive solutions. One, just pixel space systems, for instance, these as opposed to learned embedding space systems, or just any off-the-shelf vision model that has been trained for God knows what, but you still use its features to get a distance metric, like take a dyno model that people have used and feed this RGB image, or maybe anything anyone has done with digit images for any other task, like material classification, with that, versus your solution where you train this this sort of nearest neighborhood. So
yeah, it's a good question. So in the full paper, we actually have one comparison with like a standard like ResNet model for images, and trying to do the same problem. So the sort of the hand wavy things that I can tell you about this is, first thing, we're reasoning in 3D. So I think it gives us slightly better information than just working with image information, because you can essentially diagnose and split this into two parts. One is the image to 3D part. So if I swap out the sensor, I can, as long as I know the 3D part is working well, I'll know that my embeddings work. Whereas if I have an image to embedding part, then I might have to resort to training each of them separately. So that's at least how I reasoned about going from essentially point clouds to something like PointNet, for example, is a good example of what we're doing here.
as in, so even with that analogy, one could take an off-the-shelf PointNet. As in, I was just trying to understand how much benefit does learning something specific to this domain give you versus.
Oh, yeah. I would say you can still do pretty well if you just take an off-the-shelf PointNet, or right now we're using like more of a 3D spatial convolution network. But yeah, you can do pretty well with that. We just wanted to make sure that we're doing the right thing. So we did some fine-tuning with the tactile data, more of like the same contrastive learning framework. So taking poses that are far away, pulling them against each other versus the other.
And I guess the other, not so much as a question, but a part that I think we often discuss when we chat about the first paper is that, so as someone who does reconstructions from maybe vision things, it's really hard to get details, right? If I look at the keyboard, there are those ridges of the keys, which a depth model or depth pencils can't tell you very easily. But your touch sensing can presumably tell that. And to me, the reconstructions you were showing, because you converted them to depth as opposed to reasoning about normals, it felt like, oh, these reconstructions look great, but they could have also had all these details, and somehow that felt like a slightly missed opportunity.
Yeah. I agree. I think there's like one aspect of this, I think, is in the real world, because we chose these sort of herky-jerky in-hand manipulation problems, we couldn't really get the fine level of detail with the tactile sensing that you would usually get from if you're trying to like reconstruct a coin with a digit sensor or those kind of tasks. So I think if we have a more compliant elastomer and we can do those kind of things, I think it's better to incorporate. But I do agree. I think there's definitely a bit more in terms of shape that can be codified in these models.
I guess that's the other question, which was, do we really need geometry?
Yeah, that's I foresaw this. That's why even in future work, I kind of talked a bit more about implicit representations and all of those. So yeah, I think I think the main thing is we're still not sure what we need in terms of perception. So this is one of the many solutions that you can go towards. And I think it's the most immediately diagnosable and implementable one. So yeah.
Okay, so then we'll open up to the audience. Anyone has questions?
I have a quick question, James, a bit longer. For your MidasTouch, when you were doing your particle filter on like a totally smooth surface, the tracking looks really good. How are you getting that if the surface is totally smooth and you have no features? Do you have an IMU in the sensor?
Yeah, so the particle filter works on not an IMU. So the assumption is we have image information as well as we have some sort of kinematics, so odometry. So this is so in the case of, because we chose the test bed of like this finger sliding around objects, we don't really have like forward kinematics or anything like that. So we took what we get from ground truth tracking, added a lot of noise, tried to simulate that as like odometry drift, so typical to what a mobile robot would do. And then we use that as the motion model of what the particle filter happens. So that's why when you encounter like flat surface, with some motion model noise, you might see it somewhat agree to what the odometry drift is giving you.
Yeah, it looks really good. I was like, I can't figure out how that's possible.
Yeah, no. Otherwise, when you go on a flat surface, you don't really have anything to go on. Yeah.
And then another quick one. How would stuff like your NeuralFeels translate to like bimanual grippers, where instead of getting maximum hand rotation, you might get a sense and then you're into the sense? Does that break your pose regularizer? Does that break other parts of your platform? It can still work there.
So there should be tuning in terms of like there are certain numbers we decide in terms of how regularized the poses, for example. Like in these, because a lot of the in-hand rotation is a much harder task, I feel like, just because there's a lot of places where you make and break contact where you quickly slip, and those cause larger motions. So I think the way this transfers to another task, I think, is the good thing is we don't really have any kinematic constraints or we don't have any physics-based constraints. So this can just transfer to any other sensing. The only thing you need is, if you have a bimanual gripper, you need the kinematic chain to where the sensors are to use that for your tactile information. But apart from that, I think the only thing, the noise models are what needs to be tuned beyond that.
Cool, thank you. It's great.
Thank you.
Okay, fantastic visuals. This what is the this sounds like a code book for essentially poses a couple of features, right? So what is the key? Like, how are you looking up like essentially?
Oh yeah. So the question was for those on Zoom, what is the like key to sort of looking up on this code book? So it's so if you didn't have this, you're doing you're querying, like I told Shubham, like you're querying all of these points, you're getting the embeddings, and you're trying to find the nearest neighbor in this embedding space. But now, once you have, for example, information of a particle, you can just do like an SE3 lookup instead to see what the nearest embedding is there. And that can tell you what that embedding information is for all of the particles. So you're doing just nearest neighbor in like a 6-dimensional space instead.
How big is the code book for, say, the Cheez-It box?
This is, I forget the exact number, but I've sampled all of them equally to maybe 10,000 to 20,000.
Explicit code book, not like a network which gives out the value.
So it's like a KD tree that you query from.
And one more question, for the NeuralFeels, you kind of videos, but like I was wondering, how did you do such a good pose estimate for such symmetric objects like Rubik cube or the pair, for example? Because if I understood correctly, the pose estimation was being done with an ICP, probably a color ICP or something like that, right?
Yeah, so the one sort of demerit in all of this is because this depth-based tracking algorithms. If you can do well with a cube because the local sort of motion of the cube can tell you, even if it's a symmetric object, you can kind of see how it rotates. The problem that you would really face an issue with is if you have a sphere, you have something that is symmetric about the z-axis, where even if you rotate it, the depth information is still the same. But yeah, so we thought about that in that case. But then we also thought about like what we need in terms of, we don't really need to reason about how it's rotating with respect to the z-axis as long as the shape is aligned with the model of the object. Because perceptually, there's no real difference in, for example, a pair rotating about.
This is for the case where you have the CAD model of the object.
Yeah, or both, even for the reconstruction part. So the reconstruction part would be a bit harder, where unless if you have perfectly symmetric z-axis rotation, that's an ambiguity that you can't really discern. But as long as you have some, because we have a pretty like, this is not a very uniform task, so there's a lot of variability in the motion. So that actually helps us rather than, but you can, what I'm saying is you can define motions that this will fail in. Yeah,
Got it.
for sure.
Thanks so much.
Questions? It's on Zoom. If not, then yes.
It's really interesting. So did you use bundle track or that kind of ideas to get the?
Yeah, I actually have not. A lot of these came out while I was doing some of these things. So bundle SDF, for example, they're all similar flavors of ideas. So I guess some of this work was based on work like ISDF that Joe Ortiz worked on, which takes that idea of mapping with known poses and then tries to incorporate pose optimization to it. But you could use, say, something like bundle SDF, which works with visual information. But the hard part really is trying to incorporate the tactile sensing to it.
The question I was getting at is like the success of bundle SDF would kind of depend on how good, like how diverse you're moving the object.
Yeah.
I was wondering, like, when you figured out the policy which actually moves it, pre-compute the policy, like what are the thoughts that went into actually thinking about that?
Yeah, we kind of did this. Yeah, we first considered what the task we wanted to do was. We initially started out with, okay, maybe you want to teleoperate the robot to collect some data. But then we thought the easier way to automate and like scale this up to a lot of data is just to in-hand rotation. And we found all these RMA policies that work pretty well. So we kind of picked that. So we, along with picking that, we sort of grandfather in the goods and the bads of that. So there's a lot of quick motions of the object, but at the same time, you can always make sure that you're on the fingertips. So it's I wouldn't say the perception system is task specific, but like the results here are task specific. Okay, yeah. So the question was, do you assume that there are rigid bodies in the data set? And the answer is yes. Yeah, we do. Yeah. Yeah, so I can talk about more in the MidasTouch work is probably more relevant for this. So in that, for example, not exactly the rubber duck, but if you take like the sugar bucks, in simulation, they're all meshes. We're just doing something like PyRender. We're trying to get information from them. They're all rigid. But when we actually work with something like cardboard or paperboard, they're deformable to a degree. So I would say that there's some error in the post tracking with those. We didn't really quantify, or we're not sure about how to quantify those things. But I would say that that amongst all the other sim-to-real problems, that's one of them.
Okay, so if there's no further questions, let's thank Sudhu again.